Hello again. Today we're going to be looking at trigonometry, specifically the rules that apply to right angled triangles. As you can see, I've drawn a simple 3, 4, 5 triangle, which gives us our right angle here in the corner of 90 degrees, and I've filled in all the information so as we work through the calculations we can see that they hold true. The first thing we need to note about our triangles is decide on the notation we are going to use to decipher the angles and sides. A lot of the formulas we'll use an ABC. So very simply, we put a capital A, B, and C at each of the corners. It's very important that the right angle corner is the A. And this is opposite the hypotenuse because that is a factor in all our formulas that we'll show you in a second. The sides, there's normally two ways to denote the sides of a triangle. The way I normally use, or a simple way, is the capital A is here. The opposite would be a lowercase a. So in this case, C, angle C is here, the opposite is C here, angle B is here, and the opposite is B here. Very often though in books and textbooks you will see the sides would be given a description of, for example, side A, which is 5, may be called BC because it's the line that runs between BC, and this side would be AC as it's the line because as it runs from A to C, and obviously this side would be AB. For this course, I'm going to use the lowercase letters as the sides because that works in well with our Pythagoras' theorem, etc., etc. So the two quick rules I want to talk about is the three angles within a right angle triangle will always equal 180 degrees. So get that out of the way. A plus B plus C will always equal 180 degrees. Or, because this is a right angle triangle and A will always be 90 degrees, we can shorten it to B plus C will always equal 90 degrees. And in this example, you can see that 53 degrees plus 37 degrees equals our 90 degrees. This being B and this being C. Very simple equation. The next equation I want to show you is what we call Pythagoras' theorem. Basically, it says the square of the hypotenuse equals the sum of the square of the other two sides. If we write this down in notation, a squared equals b squared plus c squared. Now, the important fact to remember is that a must always be the hypotenuse. Otherwise, this won't work. If A is any other side, it won't work. Because if we're looking, I'll do an example with this first. So if we look at our triangle here, we've got 5 squared equals 4 squared plus 3 squared. 5 squared is 25, 4 squared is 16, 3 squared is 9, 16 plus 9 is 25. So we know that that's true. However, what if we didn't know the 4? Then we would have to rearrange this formula. We can't simply make 4 the A, the unknown, and work through the formula. We'd have to rearrange this formula. So if we're missing B, we would have to B squared equals, and in this case, A squared minus C squared. And again, we can put the numbers in. B squared is 16, 4 is 16, equals A squared, which is 5 squared, which is 25, minus c squared is 9, so minus 9, 25 minus 9 is 16. This is probably the number one area where students will make a mistake, and they will use Pythagoras' theorem the way it's written here and make A any of the unknowns, whereas A can only be the hypotenuse. We need to rearrange the formula to sort that. Okay, so that's the two simple equations for right angle triangles. Now let's move on to the slightly harder ones. The two equations previously showed the total of the sides, how we can calculate that, and the total of the angles, how we can calculate that. But what if we don't have all the information? Here I've used the simple 3, 4, 5 triangle again, but I've left out some of the information. In this side, we can use Pythagoras' theorem to calculate the 4, but how do we calculate the angles using the sides? Well, you've probably all heard of the term SOHCAHTOA, and it's an abbreviation or a shortcut way for us to remember that sine theta equals opposite over hypotenuse, cos theta equals adjacent over hypotenuse, and tan theta equals opposite over adjacent. Now, the problem students have is, which one do you use? Well, it depends on the information you're looking for in the triangle. And we need to be aware that the notation of the triangle has changed as well. The longest side will always be the hypotenuse. There's no question about that. But which of these sides is the opposite and which is the adjacent? Well, that completely depends on the angle that we're looking at. So let's say we're looking at angle 1, theta 1 to begin with. Well, theta 1, in this case, the 3 is adjacent to theta 1 and side B is opposite theta 1. However, if we were concentrating using theta 2, the angle here, then 3 becomes the opposite and the unknown becomes the adjacent. So these two switch between opposites and adjacents depending on which angle we use. Let's jump straight into an example. Let's try and solve theta 2. Okay, so we're looking for theta 2. We then look at what information do we have available to us on the triangle. I'll just change pens, that one's a bit thick. Well, we have the hypotenuse, and if we're looking at theta 2, we have the opposite. So we want theta, we've got the hypotenuse, and we're looking for the opposite. So we then move to our SOHCAHTOA, and only one of these formulas will contain all 3 bits of information down here. And obviously the first one is the sine. Sine theta equals opposite over hypotenuse. The other two contain the adjacent, and we don't have the adjacent in our formula. So if we write in our information, sine theta equals opposite, which is 3, over our hypotenuse, which is 5, 3 over 5 equals 0.6. So sine theta equals 0.6. If we do our transposition, we can then go theta equals, the sine comes across, becomes the inverse sine, 0.6. So theta equals 37 degrees. Okay. Now we can simply calculate 90 minus 37 will equal theta 1. But let's use these to demonstrate how these work to find theta 1. So in this case, we're now looking for theta 1. Again, because we're looking for theta 1, 3 becomes the adjacent. So we have the adjacent and we have the hypotenuse. So we then, theta, adjacent, hypotenuse, we then look to our formulas here to see which of these contains these 3 variables, and we see it's the cosine, theta, adjacent, hypotenuse. So cos theta equals our adjacent, which is 3, over the hypotenuse, which is 5, which also equals 0.6. So theta equals, the cos comes over, becomes the inverse of cos, which is our shift cos button on the calculator, 0.6. So theta equals 53 degrees. Now we can see quite clearly 37 and 53 equals 90, so we can use that as our check to make sure we've got it right. Now let's move on and find our, we'll call that B, side B, and we'll use one of the angles to find it. Let's say we use theta 1. So we have theta 1, in this case theta 1, B would be the opposite. So we have the opposite. Now we have the adjacent or the hypotenuse. We could use either one. And because we haven't used the tan yet, I'll use the adjacent. So we've got the adjacent. So we've got theta, opposite and adjacent. Well, looking down the side here, our tan theta equals opposite over adjacent is the only one that contains all 3 variables. So tan, and in this case, we're using tan 1, which was 37 degrees, equals our adjacent, our opposite, which is b, over our adjacent, which is 3. If we rearrange this formula, throw the 3 over to the other side, it becomes a times. So 3 tan 37 equals our opposite. So tan 37 equals 4. 3 tan 37 equals 4, which is our opposite. And that's just a very quick demonstration on the 3 formulas we use to solve problems on right-angled triangles. My next trigonometry will be on solving problems with non-right-angled triangles.